All right. Well, hi, everyone. Hope you're having a great time so far, friends. My name is Sven, and today I'm going to show you how a simple serverless architecture can power a GraphQL API that can handle up to 100,000 concurrent users. Now, my goal with today's talk is going to focus on practicality. I don't want to show you something theoretical or something that requires like a team of 20 engineers and 1 month to build, but something that actually like a single developer can have up and running in 10 minutes or less, and the whole thing actually can sustain production workloads. So it's going to be a very practical example that I'm going to show here, and it's going to focus on the GraphQL API and that scaling to 100,000 concurrent users. Now, before I dive into the actual presentation, just a quick slide about myself so you know who I am. So I'm Sven Al Hamad, and I'm the CEO and co-founder of Webiny. I'm going to tell you a bit more about Webiny in the next slide and why Webiny is important for this talk. But prior to Webiny, I actually spent 5 years at Akamai, one of the leading content delivery networks and cybersecurity companies in the world. And at Akamai, I consulted several large enterprises like Sky, BBC, Viacom, and others on topics of web performance and content delivery. And with that experience, I was actually doing traffic engineering for terabytes a second of traffic and scale. Now, in terms of my background, I'm actually a developer by trade. I was a developer for like 15 years. The last 4 I actually spent in the serverless space. And although now as a CEO, I focus more on the business side of things. In case you want to connect with me, reach out. You can find me on Twitter and the Sven Al Hamad Twitter handle. So about Webiny. Now, Webiny is going to be at the core of today's session. First of all, Webiny is an open CMS specifically designed for enterprise needs. It has several applications that come with it. One of them is a headless CMS. There's a drag and drop page builder, a couple of more. But the important part is that all of that is built using a framework we developed in-house, and that framework runs on top of serverless infrastructure. It only uses things like Lambda, Dynamo, S3, Cognito, and similar. There's no containers and no servers anywhere in its stack. And actually, that's going to be the foundation for today's solution. I'm going to dive deeper into that as we go through the presentation. But in case you want to learn more about Webiny, you can look at our website, our GitHub, and as with any open source project, if you give it a star, that really helps spread the word about the project and gains visibility. All right. One slide just like on the topic of serverless. I know today's conference is all about serverless, and I'm sure many people told you what is serverless, showed you example applications and use cases. I'm going to just use like literally 2 slides to tell you about why serverless matters to us at Webiny, and what are some of the direct benefits we are experiencing by just relying on serverless services for our architecture. So firstly, like we got 2 actually architectures here. The bigger one that takes pretty much most of the slide is your traditional architecture, where you have 2 availability zones. Each one has a load balancer that then splits the traffic between the compute units, and they connect into a database, and that database has a replication. So if one availability zone fails, you still have the data in the other zone, right? There's a lot of like engineering that's going on under the hood to achieve certain fault tolerance. So if something goes wrong, that your application still works. Now, the architecture on the right is just a typical API gateway, Lambda, and Dynamo. It's doing the same thing as the architecture on the left, just way, way simpler, right? And that's kind of the gist of what we see in serverless. This is a view of that same architecture, but from the perspective of responsibilities. What parts are your responsibilities to maintain, patch, manage, scale, in addition to the application code, of course. Now, the ones in red are the ones that you need to manage. And you need to make sure that they are fault tolerant, that they're always available, that they scale, that they're secured, everything around them. And those are important ones to know, because with responsibility comes the fact that you need to invest time into managing those. And on the right-hand side, as you can see, there's no reds. All of the stack is managed by the cloud vendor for us. And that actually translates into two major benefits we're experiencing from serverless, and that's higher cost savings, because I now don't need 10 DevOps engineers, so I maybe need only one. And the other thing is fast development cycles, because I can invest more time into engineering. My engineers don't need to waste time so much on bringing up infrastructure, doing the high availability, architecting and things like that, because it's an inherited thing. So this is kind of the gist that why we love serverless and why we are using only serverless services and no other infrastructure pieces when we are designing Webiny. And that's kind of going to be the focus also for today's talk. The architecture is just going to focus on serverless aspects of it. All right, so what is the goal of the talk? Now, we have a couple of requirements that we set for ourselves. And firstly, we want the full control in the stack over the business logic, authentication, resolvers. We don't want any proprietary technology that locks us in. We don't want specialized tooling that is, let's say, constrained to maybe just one cloud vendor in case we want to move to another one. We also want to have a proper security on top of our solution. So an integrated identity provider. We need to handle about 100,000 concurrent users. And we want to test the whole thing for performance with actually a database that has 1 million or more records in it. So we don't want to do, here's a hello world, an example. No, this is a proper example with proper security, proper database, something that you can see in real life and can use in real life in your own, right? And we want to build all of this in 10 minutes or under. I know it's quite a task, but stay with me. All right, first things first. Concurrency is not actually the same thing as requests per second, right? Most of our infrastructure is limited on throughput. And we actually calculate the throughput as requests per second. Now, there's exceptions to that. If you're doing video streaming and things like that, throughput is something else. But in our case of a GraphQL API, it's how many requests per second can we handle, right? So first thing we need to do is translate this concurrency requirement into requests per second. And there's certain assumptions we're going to make in this talk, but in a real life example, you would look at your analytics tools to extrapolate some of the numbers that we're going to use in our assumption today. And the main assumption we're going to make is that one user spends about 5 minutes on our website, and during those 5 minutes, they do about 10 API calls to the GraphQL API. So that is our assumption to use as a foundation to translate concurrency into requests per second. And this is an example formula that we will use. So it's the concurrency we want divided by the time on site in minutes multiplied with 60 seconds and divided by number of API calls that a single user does within that time span. This formula, assumes an ideal user distribution over time. So if you're dealing with spiky traffic or flash crowds, you will need to use a different formula, but in our case, this is what we're going to use for today's talk. And if you populate our numbers into the formula, we now actually get a number of 3,333 requests per second. There's a lot of threes in there, but that's how the math ended up. And this is one of the benchmarks we need to achieve with our solution. We need to be able to handle more than 3,000 requests a second. And that includes everything, database lookups. So essentially from a client request to a client response, that is kind of the full request response that we're looking at. So to design our solution that can handle this, there's some things we need to consider, right? And the first thing is picking the right AWS region. Some of you already know, but some might not. Lambdas have one thing called burst capacity. And that's a thing that is a hard limit. You can't really increase it. So you need to be aware of that limit. And actually that limit is different in different AWS regions. But what that burst capacity means is that from 0 to X, X being the burst limit, when you have that concurrency growth in the number of lambdas that you invoke, you will have no throttling. So let's say in Europe, Ireland, I can go from 0 Lambda invocations to 3,000 Lambda invocations concurrently without actually being throttled by AWS. But if I use, let's say, an AWS region in London, right, which fits in the other region category, I can only do 500. So after 500, I'm going to get throttled. And to get above 500, I'm going to have to wait 1 minute to get an additional 500 instances, and then another minute for an additional 500 instances, right? And you can see, like, just picking the wrong region, you can get 6 times less burst capacity. So be wary that you know about this limitation and that you pick the right one. Now, there's still a trick how you can go above burst capacity, not getting throttled, and that is by using provisioned capacity. But that costs a lot of money because you have essentially a long-lived container that is running 24/7, and you're paying for it 24/7, losing a lot of the cost savings that actually Lambdas do bring to the table. So in our calculation, we said we need 3,333 requests a second, which is higher than the maximum 3,000 burst limit. So will we get throttled? Well, not really, because if the Lambda function is able to respond in less than a second, it's freed up to take another request within that same second. So let's say if we're able to return a response within 300 milliseconds, in 1 second, one Lambda function will be able to handle 3 requests, and therefore a burst capacity of 1,000 would be enough. But to simplify things, as long as we have a response that takes less than 1 second, we'll have some additional overhead above 3,000 burst capacity to handle additional requests. But that all is linked actually to performance. And one major thing that affects the performance is the database. And that's the second thing we need to consider in our design. We need to ask ourselves, do we want to optimize our solution for writes or for reads? And do we know access patterns? Do we know how users will access our database, how the lookup queries will be formed? Right. Now we've got 2 databases here. One is serverless, the other one is not. But I'm going to tell you why we actually need the other one. Unfortunately, there's no serverless option that replaces that one. But let's focus on DynamoDB to start with. DynamoDB is a fully serverless database. It's an awesome one, right? It's got amazing performance. It scales immensely without us actually having to lift a finger or anything. But, and there's a big but with the DynamoDB, it only works well if we know the access patterns, because access patterns tell us how we need to design our tables, where we need to put our keys, and that all is tied to how the user will access the content in the database. But if we don't know the access patterns, DynamoDB is actually a very bad choice. Dynamo will constantly be running scan operations, which are very costly. And if we're talking about millions and millions of records, it just is a very bad design choice. So that's why I bring the other database to the table, and that's OpenSearch. OpenSearch, unfortunately, as I mentioned, is not a serverless database. It's a managed one, but there's no alternative that AWS offers today. So I'm pulling in one design piece that is not serverless, I know. However, that's the use case, and that's the database you need to use for when you don't know access patterns. OpenSearch will just index everything, and it's super flexible to support many, many different dynamic design patterns even. And now I'm talking about design patterns, like what is the use case where you have to support access to the database where you don't know what the access patterns will be. A typical one is actually if you're building a content management system that is headless, where the content models can be defined by the end user, and you don't know what the user is going to define, so you can't optimize for that in your code, and therefore you can't optimize for that in your database. And that's where a typical problem with access patterns occurs, and that's where DynamoDB falls short. But in our example, and I'm going to show you now the architecture, we're going to actually use both databases. So I'm going to take a sip of water and then walk you through this graph. All right. So this is the architecture what we're going to use for our solution today. And how the typical user request works is they send a request. The client sends a request to CloudFront. You can do without CloudFront, but if you want to use it in production, if you want to have a web application firewall in front of it, you do need CloudFront in front of your API gateway. And then the request hits after CloudFront hits the API gateway, and then it hits a Lambda function, where actually all our GraphQL resolvers are, the queries, the mutations, there's an Apollo server running inside a Lambda. Now, out of experience, we found a monolithic approach to a Lambda that runs our API to be way, way, way more performant than having microservices where one Lambda calls another Lambda to stitch together a schema. Essentially, with microservices, you'll often end up with change requests, one Lambda calling another Lambda, and therefore you have very, very long cold start times. It just doesn't provide us with as good performance. However, don't think about having a monolithic Lambda, meaning that your code base needs to be monolithic. Your code base can be a project that uses monorepo, where each team is responsible for their own resolvers, their own queries, and then in the bundling process, multiple packages from the monorepo actually get bundled in a specific way and deployed to a single Lambda. That's how we work at Webiny, and we found that way actually giving us the best, let's say, control over the code, the best responsibilities so that each team can control their own code base. But at the end of the day, everything gets bundled into a single function, which is way, way more performant than if we had multiple Lambdas that are called in a chain. Now, behind the Lambda, we have two of those databases that I mentioned previously. And the reason for that is that one of the downfalls of OpenSearch, I've got Elasticsearch here, but the same thing, is that it doesn't scale well with writes. If you're going to hammer 3,000 writes a second or more to that Elasticsearch, it's going to go down, even if you're using like 18x large or some ridiculously big instance. It's going to go down. It doesn't like burst writes, and it's just not designed for such an access pattern when it comes to writes. But the other database, DynamoDB, works really well when you want to write a lot into it really, really fast. So to offset the write operation, so every time you hit a GraphQL mutation that needs to write something in the database, we actually send the writes to DynamoDB, because the access patterns for writes don't matter as much for when you're doing reads. But then in DynamoDB, what we do is we call in the background a DynamoDB stream, which is another Lambda function that queues up like hundreds or 1,000 writes that had happened in the Dynamo and sends one bulk write operation to Elasticsearch. So we get this scale of 1,000 to 1 reduction in writes to the Elasticsearch by using DynamoDB and DynamoDB stream as a buffer. And then we do a bulk write in the background after that. Then with that access pattern, the reads from the AWS Lambda, GraphQL Lambda, the reads are actually redirected to the OpenSearch Elasticsearch instance. And because we don't know access patterns, Elasticsearch is really good with handling those ones. And we achieve a really good read performance as well, right? So writes go to Dynamo, reads go to Elastic, and that's where we actually get that massive scale. The whole solution also has Cognito as the identity provider. So we want proper security, verified JWT token on every request. So like we want to test the performance, the true performance, how it actually is going to behave in production. So we want to do the whole security thing as well. Now, to set this whole thing up, we're going to cheat a bit, right? As I mentioned, I want to give you a practical example that a single developer can set up in 10 minutes, roughly, not spend months and months coding that solution that I just presented. But the good thing is that that's where Webiny comes in. If you just create a standard Webiny project, that is the architecture that you're going to get. And those are the access patterns that are going to be built into the project that you're going to be creating through this command. So the whole work of creating all of that is behind the single command. And there's another command that you use to deploy and create all of the infrastructure pieces. Everything is automated. And with that, you're going to get that foundation to run that project. And how well it behaves and how well it performs, and that's kind of where I'm going to get into next. So to test the performance, we're going to use JMeter to generate the load. We're going to generate the load in a way that we first have a 5-minute ramp-up period, and then we're going to keep the steady state for 10 minutes, so just hammering it as much as we can. And there's a few things that we need to keep in mind and kind of think about, because OpenSearch, again, is not a serverless solution. You need to pick the right compute instance upon which you're going to run OpenSearch. I've tested 5 in my benchmark. I'm going to show you the results for all 5. But the other thing you need to keep in mind is tweaking that DynamoDB stream. DynamoDB stream takes 2 important parameters for you to configure. One is the batch size, and the other one is the maximum batching window in seconds. The batch size tells Dynamo how many records to keep in a buffer before you trigger the DynamoDB stream. And the other parameter tells how long to wait in seconds before triggering a DynamoDB stream. Let's say if we set 1,000 for the batch size and 5 seconds for the maximum batching window in seconds. So either we will trigger with those two parameters, with those values, either we will trigger the stream when we reach 1,000 records, or we will trigger the stream if there's less than 1,000 records, but we waited more than 5 seconds. So those are the two parameters to keep in mind, because they directly impact how heavily you're going to hammer the OpenSearch instance and how long you're going to have to wait between a write operation and a read, because the write needs to go through the DynamoDB stream into OpenSearch before it's available for the reads. So those are the things you would need to potentially configure for your own use case and tweak it to your own needs. But let's have a look at the benchmark results from JMeter. And by the way, if you're interested in any of the code and how I ran the benchmark or additional information in the graphs, they're available on our documentation portal and on our GitHub, right? So you can replicate those things for yourself. All right, after the results. So write operations. Remember, writes are determined by the DynamoDB and Lambda performance. And from like our chart here, we can see like we're sustaining about 4,000 requests a second on the GraphQL, well, even more than 4,000, like 5,000 is after the ramp up period. Because like the average response time is like 400 milliseconds, P95 is 650 milliseconds. There's some drops here. The drops were actually due to the instance where we were running the benchmark. It was capping on the CPU for a few seconds before it kind of brought back up. We didn't see any errors on the actual test on the Lambda side. But through this test, so we can see we're reaching like close to 5,000 requests a second. Although across the whole test, we were averaging like 3.9 thousand requests a second. In this test, in this 15-minute test, we inserted over 3 million records in the database. And that's in both Dynamo and Elastic. And the cost for the test, and the cost is an important thing you should measure on every benchmark test. And I'm going to get to that in the next few slides, but the cost is around 10 cents per 10,000 records inserted. So this whole test, because we inserted like 3 million records, it costed about $30 for us. Right? Now let's look at the read performance. The read is determined by the Lambda and the OpenSearch performance. And we did the read test on that same database with the 3 million records that we inserted in the previous test. So it's a fairly sustainable, like fairly large amount of records we're dealing here with. And we're actually kind of able to sustain roughly 3,500 requests a second. Within that, we served about 3 million records within a 15-minute period. Now, the average response time was less than 500 milliseconds, but the P95 was 1.3. The P95 was heavily affected by the ramp-up period. Because we, again, were able to sustain over 3,000 records, 3,000 reads per second, without actually any errors of throttling happening, we were achieving our goal of 100,000 concurrent users. So both on reads and on writes, we can handle 100,000 concurrent users with this solution. Now, there's a bit in-depth information here I want to share about the OpenSearch specifically, and that's we tested several different OpenSearch instances. And we tested everything from T3 small to C5 18x large, right? Why it's important that we ran through this test is, well, first of all, we need to understand what instance can achieve what throughput, what response times and similar. But another really important test was the cost test. And we can see in our cost test here that tests D and E actually have the same cost. And that cost is looking at the whole stack, right? But how could that a test D have the same cost as test D, while in test D we're using a 4x large, while in E we're using an 18x large that costs 8 times more, something like that? The reason is that the response times were faster. And because response times were faster, we used way less compute time on Lambdas. Therefore, we saved a lot of money on Lambda functions, and that nullified the increasing cost of a larger Elasticsearch OpenSearch instance, which is a super interesting one. And that's kind of where I'm going to get to my conclusion, right? Keep the databases in mind when architecting for performance, especially when it comes to access patterns, knowing or not knowing those, right? Also, when you're evaluating your infrastructure pieces, don't look at them in isolation, because somebody might see, oh, I've got an 18x large OpenSearch instance that is utilizing only 20%, that is utilized only 20%. Let me scale that one down. But the moment you scale that one down, your Lambda response times go up potentially. And then the cost savings you had in saving money on the OpenSearch instance, actually, you didn't save much because your response times went up and your Lambda function cost went up. So make sure that when you're looking for, especially serverless infrastructure pieces like Lambdas, that they are heavily dependent on other infrastructure pieces, and their compute times directly relate to your costs. So make sure to look at the whole stack and measure the whole stack, right? So to just quickly wrap it up, we looked at how a production-ready serverless architecture looks like for a GraphQL API that can scale and sustain 100,000 concurrent users in both reads and writes. And we looked at the important questions we need to ask ourselves when designing a solution, like picking the right database region, picking the right database. And we learned that it's super important to measure both performance and cost when doing benchmarks. So I hope you enjoyed today's session. And in case of any questions, you can ask them here in the chat. Later on, you can always reach out to me via Twitter as well. And again, if you're interested in learning more about Webiny, installing it yourself, you can look at our website and our GitHub. Everything is open source and free, so you can kick off a project on your machine in a matter of minutes. Finally, we're looking for brilliant engineers to join our team, so we're hiring. And if you're interested, again, just give me a ping or just go to our website. Hope you enjoyed today's talk. Happy to take some questions now. Thank you.
First of all, thank you, Sven, for your talk. And I will ask in the room, are there any questions? Yeah, there is one. Just a second.
Thank you, Sven. I have a question regarding the architecture overview. Maybe you can go to that slide. Maybe I missed that, but there are some annotations which I didn't get. So A, B, C, D, A. So
oh, yeah. There's another A that should be there. Those annotations were just markers for visual markers, nothing important to kind of point out. But was there any kind of confusing part about the architecture specifically that you want me to explain a bit more? I'm happy to.
So yeah, the Lambda part is quite interesting. So is there just a single Lambda which handles the request to the Dynamo? And I think it's a GraphQL resolver handling Cognito. That just, I cannot imagine that this is just a single Lambda.
It is a single Lambda. It took some engineering to put it together. And that single Lambda, like I mentioned, when we were designing Webiny, we actually started with a proper microservices architecture, multiple Lambdas with schema stitching. So every microservice exposes its own part of the schema, then a main GraphQL Lambda in front of it that stitches all together, communicates with bunch of services in the background. Looks nice on the graph. In production, you just constantly are facing performance hits because of multiple cold starts from multiple sites. Let me give you an example. Let's say you have one Lambda that controls the user service, another Lambda that controls, let's say, content, like blog posts. And let's say you want to retrieve a blog post and know the author, right? So you have to talk to both services. So in the microservices architecture, you would hit a main GraphQL Lambda, which would then understand, oh, I need to get the user from this microservice. Then it would go to another Lambda, wait for its response. Potentially, maybe there would be a cold start, because now you're splitting all of your requests across multiple Lambda, not funneling them all into one Lambda to keep it really, really hot in terms of performance. And then once that response from the user service comes back, it has to go to another Lambda to retrieve the blog post content. Again, might suffer from a cold start, and then the response is all put together in that main Lambda and put back to the user. We didn't find benefits with that. We just didn't. We were just having performance issues with it because our code is structured as completely decoupled code in mono repos. But when we bundle it through Webpack, we actually bundle it all together that gets deployed to one Lambda. So our engineers are still able to work in isolation without actually kind of causing problems between the teams. But having it in the monolithic Lambda, just performance is really, really good. So that's from like literally our real life experience.
Cool. Thank you.
Any other questions? No. I see happy nodding faces. So no other questions? Okay, there also aren't any questions in the chat. So I guess that concludes your talk. Thank you, Sven, for being here today. And if there are any questions coming up later on, they can always contact you, right?
Yes, I'm available on Twitter or through Webiny website. Yep. I'm around. So
great.
All right. Well, thank you for having me.
Yeah,
I hope I managed to pass on some knowledge. So enjoy the rest of the conference.